I'm Dave Jenkins from Heriot-Watt at the Urban Energy Research Group. I'm going to talk today about building modelling, which is usually quite a dry topic, so I'll try and make it interesting. But in context of what's happening with buildings in the future, we'll start off with maybe a bit of bad modelling and hopefully finish off with something that's a bit more interesting. Okay, so the Urban Energy Research Group, where I'm based, we're a small team of researchers and academics looking at energy in buildings in the most general sense. So we do a bit of social science. We're primarily centred around engineering and technical disciplines though. Building simulation, low carbon building design a bit more generally, fuel poverty, and in the last few years in particular climate change adaptation, so doing things to buildings to stop them failing in a future climate in simple terms. Been going since about 2004, 2005. And we're also part of the Royal Academy of Engineering Centre of Excellence in Sustainable Building Design within Heriot-Watt School of Built Environment. So, a multidisciplinary research group around energy in buildings. So the talk today is about building modelling. So if we sort of take a step back and look at things a bit more generally, the task, in a very sort of crude sense, is to produce new and retrofitted buildings to radically reduce carbon emissions by some future date. I didn't want to tie this to some net zero carbon buildings by 2016 because these targets are always very fluid and zero carbon changes from one month to the next. So whatever we're going to do is going to be a radical change if we're going to succeed by some future date. The mechanism from a point of view of building modelling is that we have some way of standardising building performance that can be used on millions of buildings in the UK in a way that is somehow fair, so that we're assessing buildings in a standardised, repeatable way such that we have some way of comparing that building over there with that building over there. That's the intention though. So the result does have a question mark after it because it's not entirely clear whether we're actually doing this at the moment. So a fair energy assessment of our built environment that provides coherent and consistent advice to both designers and occupiers. So we're getting good advice on what to do to that building if it already exists, or good advice on a new building design, what technologies we should use and so on. So are we currently using models to do that in an accurate way? So that really partly describes why we're using models, and it's certainly true that buildings have never been more modelled. Energy performance certificates, of course, the Green Deal, with those two in particular, the reliance on what we call steady state models, which I'll come to in a second, but very simple compliance tools that we use to decide whether a building is good or not. And the Green Deal I'll talk about a little bit more in a second. And also even things like fuel poverty figures, numbers that we tend to treat as real numbers. You know, the number of homes in the UK that struggle to heat their homes, this 10% definition of fuel poverty that some people might be aware of. That's based on modelled thermal performance of buildings. It's not based on real heating bills from homes. So we're hugely, sometimes even in a way that we don't realise, we're hugely reliant on modelling. So it's perhaps a good idea to check whether those models are actually giving us sensible answers or not. So we must be careful not to use modelled outputs as replacement for real data. Unfortunately, that's something that we do quite a lot. And models, in their defence, are most effective when used to represent the effect of change. So if we can understand how a building is currently working, then there is a role for models to describe some vector of change based around climate change, technology change, behavioural change. They can perform a role if we use them properly and if we use the right model. And I'll draw on that later on. So building modellers, we tend to split models into two basic forms, and some of you might be familiar with this categorisation. On the left we have steady state models. So these tend to be calculating building energy performance over quite a long period of time, quite averagey. We sometimes get annual outputs, at best monthly outputs for, say, the energy performance, the energy consumption of a building. Whatever time frame we're looking at, that particular time frame doesn't really know what happened on the previous time frame. Conversely, dynamic simulation, if you're doing, say, an hourly simulation of building performance through a dynamic software, then the calculation for hour number 3 knows what was happening for hour number 2. So it's dynamic. You can apply transient profiles through these buildings, and actually you're a bit more flexible as to your description of the building within that simulation environment. So we tend to use dynamic simulation for fairly detailed assessments of individual buildings. If you want to do something quick and dirty, you tend to go the steady state route. We see this in compliance tools used for rating a building. Is it good, bad somewhere in between. Nothing kind of more clever than that really. Ballpark estimates of energy savings. Using the accreditation regulation, building compliance. And often if you get estimates for, I don't know, the effect of insulating 1 million dwellings across the UK, that'll be based on some kind of steady state calculation applied to lots of buildings at the same time. You can't do that with dynamic simulation because it would take too long to simulate millions of buildings. So it's a different type of modelling, and through this presentation I'm going to refer to building models, but always remember there are these two different paths to building modelling. But there's still things, bad models, whatever path you take. There are bad models and also bad modelers, which I'll also mention in a little bit in reference to the Green Deal. But a model can be wrong and still be useful. We might be familiar with this term performance gap. I think it's been mentioned already today. So the difference between what a model says a building is doing and then the actual real energy bills. And that is an important research area, this performance gap. But I think sometimes we get so obsessed by that performance gap that we think the best model will be the model that gives us a zero performance gap, and that's not true. We should be assessing the models by what's going on under the bonnet as much as what's coming out the back end. So actually you can miss your prediction, you can get your energy bill wrong, but actually inside that model, if it's a good model that's properly designed, it's still telling you something about that building that you can use to inform your design. Of course, there are plenty of examples where the model sent you on the wrong path entirely, and it could be a combination of bad model and bad modeler. So some actual results. This is a particularly interesting report from a couple of years ago by Jones, Lang LaSalle and Better Building Partnership. So I don't know if you can see these bar charts, but on the left we have the results of the compliance test of that building, so the energy performance certificate, A, B, C, D, E, F, G, color-coded. Then all these grey bars, these are actual measured energy consumption in kilowatt hours per metre squared for a whole range of public sector buildings. So it's really a comparison of display energy certificate output with modelled energy performance. So we have what the models think they are on the left in terms of what category they are, and we have the actual energy consumption on the right in those grey bars. And this might be a shock to no one, but the average E-rated building, which is shown by this red line here, so this is the real average energy consumption of E-rated buildings, was actually slightly better than the average of the C-rated buildings. Or more to the point, if you go through all those buildings, if we were using a trustworthy compliance tool, you'd expect the energy consumption of your G-rated buildings to be over here, so you've got a nice gradient as you go up to your supposedly more efficient buildings, but actually you can see almost no correlation at all between what the energy performance certificate says the building is and what actually came out from the real energy data.
Are those offices then?
These are public sector offices, yes. All non-domestic, sorry, I should have said that. So that's not a great start for our use of building models. This is in the domestic sector. This is from Affinity Sutton Future Fit report. Again, a really quite interesting report. It was particularly focusing on what might go wrong with the Green Deal. The actual data was from 2012, I think, so it predated the official launch of the Green Deal. So what we have here, something like 50 dwellings. They're all going to be retrofitted, a whole host of different retrofits. Some just had lighting done and a bit of insulation. Some had slightly more expensive retrofits carried out. So, unsurprisingly, through the models, if you just look at the blue charts, first of all, this is showing what the models predicted would happen after the retrofit, so how much energy would be saved. And unsurprisingly, the model says they'll all save energy as a result of these retrofits. In green, you've got the actual measured energy saving, pre and post refurbishment. And once again, you see absolutely no correlation at all between what the model said was going to happen and what actually happened. 2 points. In some cases, in fact, nearly half of the buildings were using more energy after the retrofit than before. Now, of course, we have to bear in mind, we don't want to blame the model for everything. There are rebound effects. There are things that happen after an installation that you can't really blame the model for. So people might turn their thermostats up. People might behave in a different way. The weather might have been slightly different. So we must be aware of all these things when we're doing pre and post installation refurbishment comparisons. But I think we would be hard-pushed to blame all of those differences on non-modelling aspects. Something is not quite going right there. These are all modelled with SAP and SAP-based models. I presume people are familiar with SAP, Standard Assessment Procedure for domestic buildings, SBEM for non-domestic buildings. That's what gives us these colour-coded stickers that we can put on the wall. So these are the models that are being used, steady state, simple compliance tools, and they bear very little relation to actual energy bills. It would appear from this sample. So what are the implications of this? I mentioned that models can be wrong but can still be useful. So just because they don't match up, we don't necessarily want to assume they're completely useless yet. Well, the first implication for the domestic sector, and later on we might see this problem in the non-domestic sector if it takes off. The Green Deal. So the Green Deal is, I'm sure everyone knows what the Green Deal is by now, but the idea being that someone who's of variable training comes to your house to try and persuade you to sign up to a loan for thousands of pounds that you don't really want. Very few people, as a result, have signed up to Green Deal loans because, well, for various reasons. So, of course, the problem here is that you have someone who's maybe been, to be Green Deal assessor, you can go on a 5-day course. Absolutely no background in buildings, go on a 5-day course and you're a Green Deal assessor. You can go around to someone's house and say, I think you should sign up to a £10,000 loan to get a low-energy retrofit for your house. So that's the training you need. So that's a bit of an issue, first of all. On top of that, they're using SAP-based models. Well, we've already seen the SAP models don't really give you reliable advice, don't give you reliable outputs for how various technologies are going to perform. So you've got someone with poor training, with poor understanding of buildings, with quite a poor model coming around your house telling you how many thousands of pounds you should sign up to for the next 25 years at 7, 8, 9% interest. So that's obviously an issue. Partly a modelling issue, partly also a assessor quality issue. If you look at probably more the non-domestic sector, organisations thinking about paying for more low-energy design or more consultancy or just making different decisions. It might not be as simple as paying more money. They're just making decisions based on wanting to get one of those A-rated or B-rated buildings instead of their E and F-rated buildings. But then they look at their real energy bills 12 months on and they find actually their energy use is just the same as their supposedly inefficient building half a mile down the road. So why have they gone to all this trouble to sign up to a supposedly lower energy building? Slight caveat to that is that we did a study a few years ago speaking to energy managers of quite large organisations, and actually their energy bills are a very small fraction of their total running costs anyway. It's not always the case, it depends on what their line of business is, but very often actually they're more interested in getting that A or B sticker on their wall because they think that will be quite good PR. The actual size of their energy bills are not a huge concern to them anyway because, as I say, running costs, it's sometimes just less than 1% of their total running costs, their total energy bills. And of course, forming policies and subsidy programs around these technologies, well, we're judging these technologies from these very, very simple models. Is probably ill-advised as well. We might end up backing the wrong horse. Perhaps one of the biggest problems from all of this, well, the biggest implication is the use of compliance tools for design. So what often happens is you might have a great modeller, really understands their buildings, they know what software they want to use, they know how to use that software, but actually they need to get to compliance first and foremost. So they use the compliance tool, their SAP tool or their SBEM tool, and they know that certain technologies are going to give them the points that they need to get their energy performance certificate rating that they want. So they're actually using that compliance tool to choose technologies. They're using it for design. They'll use the design tool later on, but first and foremost, they will use that compliance tool to make decisions on what technology should be in that building, which isn't what it's for. That's not what a compliance tool is for at all. So using SAP and SBEM effectively to design buildings. So to kind of finish on a slightly more positive note, and some perhaps more useful ways of using modelling, looking at future visions for buildings in Scotland. As I say, if we do find an empirical baseline for a building, so we've measured that building as best as we possibly can, so we know how it performs, we know what's going on with that building, we still might want to model it just to understand how it's going to perform in the next 10, 20, 30 years. To take into account climate change, various retrofits, building design changes, changes to regulations and legislation and so on, and of course behaviour change. So can we use proper models? By proper I mean not SAP or ASPEM, something a bit more flexible. So dynamic simulation software to capture this variation so that we can have a pretty good guess, a pretty good estimate of how that building is going to change over the coming decades. So I'm going to give you two examples that we've been working on at our research group. One's called Low Carbon Futures, the other called Ares. So both projects are attempting to use novel forms of modelling to fill some kind of gap in our knowledge. And by definition, because we're looking to the future, we don't have empirical information about what's going to happen in 20 years' time. So this is why we feel we need to model. So the LCF project, first of all, finished last year, effectively, funded by EPSRC. And we're looking at, we did look at investigating methods for using the latest climate projections in building simulation. So complex dynamic building simulation. For those of you that haven't come across UK CP09 before, it's a probabilistic form of future climate projection. So what that means is, from a building modeller's point of view, rather than you having a single climate file telling you what the future might look like, you have hundreds, possibly even thousands of climate files giving you a spectrum of probabilities for what that climate might look like, which is a complete nightmare for a building modeller who's trying to reduce the amount of input they're using. So that was essentially the problem that we were trying to deal with. The full report is on the project website, which goes over the detail. But the three main questions we were trying to look at, first of all, how can building simulation use a probabilistic climate database of this type? Second question, how can this be used for designing adaptations for buildings in the future? So once we've somehow accounted for those future climate projections, and we kind of know what's going to happen, or we kind of think we know how climate's going to change in the next 20, 30 years, how do we use that to design changes to the buildings to stop them overheating or to stop cooling loads getting too high and so on? And how can all the above be incorporated into a method that's actually useful for industry? Because we can do stuff that we can feel quite smug about academically, but then if it's completely inaccessible and doesn't actually give output that's useful to industry, then there's not really much point in us doing that. So first of all, well, to answer the first question, we set up an emulator. So this is just a shortcut that means instead of doing thousands and thousands of dynamic building simulations for all these different climates, you only have to do one. And then we have a little kind of bypass emulation software that actually runs all the other climates through automatically and then converts your one simulation into hundreds or thousands of simulations. So that's the first thing we did. To answer the second question, well, it's a combination of using appropriate software. So it's looking at existing design practices and trying to piggyback on top of that. So we look at software like IES, for those familiar with building software. Could have used something like TAS as well. So something that it's already used within the design process, and we're just trying to give someone an extra button to press to get a bit more output. And one thing they liked was this. This is what we call our future overheating risk matrix, slightly grandly. It's just a colour plot. So over on the right, we have percentage chance of failure for a particular building. So what we've done here, we've defined an overheating criteria for this building. We've judged that based on the hourly simulation that we've done in the dynamic software. So over here, this is the chance of the building exceeding that overheating threshold. We've used quite a simple overheating threshold of percentage of hours above 28 degrees, which is a fairly crude overheating threshold, but you can put something a bit more clever into there as well. Then over on the left, we have 4 different adaptation scenarios, no adaptation, and then 3 different adaptations, where these can be perhaps external shading, reducing internal heat gains, just carrying out a number of things which you think might reduce the chance of that building overheating. For the current climate, this particular building doesn't overheat or has a very low risk of overheating, so that's fine. So it's been designed properly for a current climate, first of all. That's sometimes quite a major assumption to make, but we have made that assumption. We then run it through all these different climate projections, 2030, 2050, 2080. These refer to low, medium, and high greenhouse gas emission scenarios. And you can see, if you don't do anything to that building, it's almost certainly going to overheat according to our models in the future. So you might then start running these different adaptations through it, and you see how that overheating risk gradually decreases. And of course, if you've got good cost information for these adaptations, you can start to do that cost to risk kind of analysis. So is it worth me spending, I don't know, an extra £100,000 on adaptation number 2 just to ensure that the building's still okay in 2050, or am I only concerned in 2030, in which case I'll stop at this point, perhaps. So there's more detail in the report of that. You'll see we've gone through various case study buildings. This is the kind of information we've sort of produced these fact sheets of what the building's all about, how we think the building's going to perform, and then these are more detailed risk, probability and risk graphs, trying to describe whether we think that building's going to still be okay for various future timelines. And then finally, the Ares project, which is currently ongoing. This is a little bit different. So what we're concerned with here is the sort of general, or the wider energy system that the built environment sits within. So we're interested in the energy demand that's being produced from a given chunk of built environment, but we're also interested in how that talks to the wider energy supply industry and the energy infrastructure. So University of Edinburgh is doing the supply side stuff, we're doing the demand side stuff, so we're focusing on the buildings. Projects essentially split up into this way. So energy supply, so what's going to happen over the next 30, 40, 50 years to large-scale generation in particular, but also microgeneration. Transmission, distribution, this can be affected by, for example, climate events, wind, high temperatures can affect actually the efficiency of that distribution of both electricity and gas. And then our focus at Heriot-Watt is this energy demand. What's going to happen to the shape of an energy demand profile in the future as a result of all these kind of externalities? And the sort of typical problem for us in this type of project is how do we make the jump? We want to get to this point down here where we're kind of approximating the energy demand of lots of buildings at the same time. But we also want to maintain the detail we get by doing individual building analysis of individual technologies. So you want to make a kind of jump. There's an upscaling procedure somehow to get from one or two buildings to hundreds of buildings. Because you can't talk to the energy supply, sort of the energy networks, until you get to this end. They're not interested that one person's turned their kettle on at 9 in the morning, but they might be interested that everyone turns their kettle on during a World Cup final, that sort of thing. So it's a kind of upscaling issue. And just very quickly, I haven't got time to go into the detail of all this, but this is an IES simulation environment, which might, even for those who use IES a lot, this might still look quite foreign. What we've actually got here is lots of different building models, all within the same simulation environment, so we can simulate them all at the same time. But within each block, we've got a fairly kind of crude description of buildings, but enough information in there to describe sort of thermal performance. So we can play about, obviously, with U values and so on, but we can also play about with heating systems, ventilation systems, and different heating control schedules, and so on. And we can then, and this is just perhaps a selection of constructions that we might choose to use within this kind of sandpit of different buildings, and then we can post-process that, so we can say, right, well, we've simulated all these different building types simultaneously, but the particular street that we're looking at has a certain combination of buildings. It has maybe 10% of those, 20% of those, 15% of those, and we can sort of aggregate them together so that we end up with some form of aggregated thermal demand for that specific mix of buildings. And we can then start thinking about, well, what would happen if we did a bit of fuel switching? So this might be gas heating for all these dwellings, but maybe we're expecting 30% of them to have air source heat pumps in the future. So we can do a bit of fuel switching, see what happens to the thermal demand, but then also see what happens to the corresponding electrical demand. I'm not going to go into the electrical demand process that we're carrying out at the moment. This kind of takes a bit more explaining, but the end goal is really to have lots of different future energy demand scenarios. So this is actually an electrical demand profile aggregated for about 50 dwellings. So when you do this aggregation procedure, you get quite a smooth profile. So this is something the National Grid would be fairly interested in. This is the kind of image that they talk to. So that's current, but if we start running in lots of future scenarios, putting in maybe future climates, maybe, again, I mentioned heat pumps. Well, heat pumps might be operating around about this time, so they'll suddenly give you a gradient of electrical demand that wasn't there before. So you start asking yourself the question, well, is this jump a problem? You might have saved energy or carbon in a very simple estimation because you've reduced lots of gas by putting in these heat pumps or whatever technology it might be. But you have created a new peak that wasn't there before. And from the energy supply point of view, from National Grid point of view, they kind of need to know what that magnitude is. When is it jumping and how much is it jumping by? So is that a problem for the current infrastructure? Can they cope with that? Is it fine? It doesn't exceed capacity limitations on the low voltage or high voltage networks. But will it be more of a problem if we then look at future energy infrastructure where we have a different energy mix? We have different types of technologies actually trying to meet that energy demand. So that's really the kind of level that we're trying to talk to for the ARES project. So just to finish up, models do absolutely have a use in helping us project various future scenarios, particularly for climate adaptable, low carbon design. Things are changing, and we want things to change because we want to reduce our carbon emissions. So in that kind of environment, there is a role for models to play, without a doubt, providing they have a proper grounding in building physics. And of course, in an era of more stringent building regulations. But oversimplifying the process limits the robustness of the advice. So if we are starting to use these SAP models and SBEM models to actually design buildings, then we shouldn't be surprised if they push us on the wrong path, because that's not what they're for. But partly because of things like the Green Deal and this obsession with compliance. That is the path that we're currently going down. And models should never be presented as real, which is a note to all Green Deal assessors. You do worry when, as I say, you have these people coming into homes and almost effectively guaranteeing savings on your energy bills if you sign up to quite high capital costs or quite high loans. They don't know this. No one can guarantee energy savings if they're based on SAP or for any other model. And ultimately, I think we need to find methods for models to complement real data. And to finish on a more optimistic note, I mean, real data is now more accessible. You have things like the embed database from Energy Saving Trust. So we now have empirical information that's telling us how buildings perform in a way that we didn't 5 years ago even, or certainly 10 years ago. So we are now getting that data, but I don't think we've quite worked out how to use that data in a useful way. So that's maybe the next step. Thank you.